All right, I guess I am recording. Sorry, checking to make sure it's actually working. So here we are. This is break week for me. I'm recording this this is Thursday. Light snow coming down outdoors. But a few days ago, Dora and I got to go out for a walk. I'm down in Kingsburg at the moment, and we went for a walk in Felton South. And Felton South is if I turned myself around from where I'm looking at the moment, or where this picture is, I'd be looking across quite a distance away, a bay that would be over towards Lunenburg, would be in the distance for me. Lunenburg is actually in a very, very long inlet that comes in from the Atlantic. And it's sort of at the end of an inlet on one side, and Felton South is on that further out towards the ocean, but still reasonably well sheltered. And there are a number of lobster boats that tie up there. It's a nice little spot. So let's get ourselves started here. So hopefully you had a good break, and hopefully you remembered to do the Chapter 6 quiz. If you didn't, you should be contacting me ASAP. So discussion 6, that's due on Wednesday. That'll be, why do we like linear models? That we're obsessed with studying linear models, and that's what we'll be focusing on this week, is carrying on from a simple one to getting into more complex ones. And test 3 is coming up on Friday, so it's going to cover chapters 5 and 6. So that was box and whisker charts, correlation and scatter diagrams, and simple linear regression. You've got quiz 7 on chapter 7 coming up on Saturday, and I say assignment 3 will be posted soon. I'm working on it right now, and it'll probably be posted by Monday anyway. So by the time you're seeing this, I'd think. So what would February 27th be? I guess it's no-brainer day. And stop overthinking things. Take it easy, relax a little bit, and particularly relax your mind. Life is too complicated, too busy, and we shouldn't be making it busier, more complicated. And it's International Polar Bear Day. And if you've been following things, that's worrisome as the amount of ice shrinks in the north. Polar bears are finding life a lot more complicated. But, anyway, what's coming up this week? There are a couple of workshops going on. On Tuesday, there's one on procrastination, and on Friday, one on time management. Both of things are our biggest problems for everybody, not just for students. Everybody struggles with those. And I understand there's a student leadership conference on Saturday, and I don't have any idea what that covers. But looks like maybe something you'd like to look into. And I should mention that this week, I think it's Thursday, it is, there's the annual business dinner that the Commerce Society puts on. And one of my students from back in the 80s, Joyce Carter, will be presenting there. She's done very, very well for herself, and for the last number of years has been the CEO of the Halifax International Airport Authority. You can do all kinds of things with an accounting degree, as you can do all kinds of things with every other type of degree too. So last class, we started in on regression analysis, and it's the most common technique used for value estimation. Value estimation is predicting a number. And that you build a formula, and the coefficients of the model, it's a linear formula that so it's very simple form. So just a number times a variable plus a number times a variable and so on. And those numbers are often used for causal analysis to try to explain how certain inputs affect the outputs that take place. Now, the input variables are often called independent variables. Statisticians like to call it that. In data mining, they may call it a predictor variable. Some people will call it an explanatory variable. It helps you predict or explain what's happening with your target variable or dependent variable. That's your Y variable, the one on the vertical axis, that it depends upon what's on the x-axis. So your independent variable. So in statistics, we would generally call it a dependent variable, but in data mining, they frequently call it a target variable. Oops. Now, in building these models, we normally use a technique called ordinary least squares. And it's an approach that finds the line that goes through the scatter that minimizes the average square distance between where the line is and where the dots are. So up and down, what the prediction is, that's the line, and what actually happened, how big a gap is that? And let's square that distance, and that puts a much bigger penalty on big errors than on small ones. And then average that out. And so we'd like to minimize that average squared error. So we're going to be starting with building simple models that are linear, straight lines, and between our explanatory or predictor variables and the target. Oops. And it's generally a good starting point. Don't make models more complicated than they have to be. The model quality, performance of the model, we usually look at in terms of the standard error. In a sense, that's on average, how big a gap is there between the line and the points. And most of the time, you don't get predictions that are more than 2 standard errors away from the actual values. So most of the time, we're within 2 standard errors. The rest of the time, we're not perfect, but we're hopefully not too bad. So if that standard error is quite small, then your average prediction error is relatively small. Another popular measure is called R-squared, and it's a measure loosely of if you're the alternative to using this model that you built is to have no model. So one extreme or the other. Your plan B is just guess. And the R-squared measures how much better you are using the model than guessing using just the average value of Y. So average credit card balance as a prediction. And it's how much you've been able to improve things. So if you made 100% improvement, then you've reduced all the error that's present. If you've got an R-squared of 50%, then you're 50% better in a sense. It's they say it's a measure of the percentage of squared variation in the target, credit card balance in our case, that you've been able to explain with your model. I generally don't like that term, but that's what's commonly used. Just a bit of a caution as we go forward in building models and thinking about things. We're using correlations and looking at relationships between variables. And just want to warn you about using time series data. A lot of the data we get in the business context and economics is data that's collected over time. And what you can often get with time series data is 2 variables that are correlated with time. So they both vary in the same fashion over time, but are unrelated to each other. But if you plot them together, it looks like one is causing the other. This is taken from a website. I think it's noted in the text. Maybe noted on the bottom of my slide. TylerVigan.com. And here is Japanese cars sold in the US and the number of suicides caused by crashing a motor vehicle in the US. And you'll see that they seem to line up with each other. They're very highly correlated. If I plotted one against the other, it would look like a straight line. That door is behind me and trying to slip out the door. So be cautious when you're looking at stuff. So correlation isn't causation. It just says that they're both varying together. So the other thing, though, I should point out is if you don't find any correlation, does that mean there's no relationship between them? Well, maybe, maybe not. That if I was, and you're doing this type of thing in your assignment, that I'm asking you to look at, I think I had asked you in your assignment to do a scatter plot where you'd look at the number of hours you were studying and looking at your grade point average. And you'd think, well, if you studied more, you should get better grades. But when you look at the scatter plot, it doesn't look that way. That this is not using your data, but previous year students, but the same result happens. It's got an R-squared that's very, very low. That and similarly, if you might argue, if you had to work a lot, then you might it might affect your grades. That's a common belief anyway. But if we look at the data, that people that work a lot of hours, their grades go down marginally, but by and large, it doesn't look like much of a pattern there. Correlation is very, very weak. The R-squared in both models is very, very low. So what's going on here? Is there no relationship between these? Now, we've got a couple things. If you were building this as a formal model, it has a slope between studying and grade point average that's 0.012. So for every additional hour of studying, your grade point average is expected to go up by 0.012. So if you studied an extra 10 hours per week, then your grade point average might go up by 0.1. So you might go from a 2.8 to a 2.9. Not very much, okay? And the standard error of this is very, very small, 0.002. So even if we go out 2 standard errors above and below, I'm saying the slope of that line, okay, it may not be exactly 0.012, might be as low as 0.008, might be as high as 0.016, but it's still positive, so it's still going up, just very, very slowly. Not a big payoff to studying a lot, it seems. And with working, it goes in the opposite direction, as you might expect. That if you work an additional hour, your grade point average will go down by 0.002. Or if you're work for an extra 10 hours a week, it says your grade point average would go down by 0.02. So you'd go from a 2.90 to a 2.88. Gee, that's not much of a change, is it? So it doesn't look like working affects your grades. Now, remember the slope is negative. When I say down, if you looked at the coefficient in the previous slide, you'd see it was negative. But it's a very tiny amount. The standard error is also very, very tiny, which suggests we've estimated it very, very accurately. But if you went out 2 standard errors, that or even if you went out, if you went out 2 standard errors, then if you went up by 2 of them, so if you went from minus 0.002, and then you're going to go out to, that would be going up an additional 0.008. Anyway, you'll get the slope could be plus 0.006 or minus 0.01. It could be positive, it could be negative. That would suggest that working more, if it was positive, working more hours drives your grade point average up. Or work, if it's negative, then working more hours drives your grade point average down. We don't actually know which direction it goes in. So does working more increase or decrease your average grade point average? Don't know, one way or the other. That we don't know what the impact is. That the correlation here is effectively zero, that there is no relationship here at all. So when you've, if you went out 2 standard errors and you switch from positive to negative or negative to positive, it means that variable isn't telling you anything, that you don't know if the line's going up or going down. So with both of these, there's really little or no relationship. Is there any other explanation that could be happening here? I'm presuming that grade point average depends upon how many hours you study or how many hours you work. But could the relationship go the other way? That if you've got a low grade point average, you would probably be motivated to improve it. And you would probably do that by studying less, or sorry, studying more and working less, which sort of goes in the opposite direction. So that low grade point averages should be associated with higher amounts of studying and lower amounts of working. Whereas a minute ago, we were thinking of it the other way, that more studying is associated with higher grade point averages and more working is associated with lower grade point averages. But if I think of it the other way around, if your grade point average is low, you're going to study more, work less. Or if your grade point average is quite high, you might think, I can study less and I can work more. So it goes the opposite way. So it's possible that lines they're both going up and they're going down at the same time because we're behaving differently. That it isn't A causes B or B causes A, that A and B, we self-regulate those sorts of things. And if that's happening, the type of scatter you're going to get is scatter around 2 crossing lines. It's just going to be noise. So maybe that's what's happening. Don't really know. Okay. That this is observational data that we've got. Okay, it's not a controlled experiment. So if in a controlled experiment, I could take someone and change their behavior, or what they're doing, and maybe see what happens with their grade point average and see, does it go up or does it go down? But in practice, we don't have that. So we've just got observational data. So be careful when you're dealing with this. We can see a pattern that might be caused by something else, like we saw with time series data. And if we have no pattern, it could be that the 2 variables affect each other. It isn't a one-way relationship. It could be 2 ways. It's a lot more complicated than it first looked. So tests coming up. Here are a couple of sample questions that we could use. These are from old tests. So here's a model that tried to predict students' grade point average based upon their high school grades. And we looked just at students from Nova Scotia high schools that came into St. Mary's and what happened during the fall term. Took that data, built a model, and the model ends up being GPA is minus 3.77 plus 0.0787 times the high school average. Okay, so if you had a 90% in high school, we would expect you to have, the model says 3.31 as your grade point average in university. So how to interpret that? So am I saying that the grade point average of most students with an average of 90 will be at least 3.31? That most students, would it be exactly 3.31? The average of all students with an average of 90 would be approximately 3.31, or 29.7% of students with a high school average of 90 will have a GPA of 3.31. Where did D come from? Well, if I look up here, I've got an R-square of 0.297. 29.7% is my R-square. Anyway, what's the correct interpretation? R-squared doesn't tell you about percentages of people. It's this general quality measure. So D doesn't belong here. My model is telling me where a line goes through a scatter. So looking at 90 and I go up to the line, I'd get 3.31 coming across. The line should be representing the average of all students with a 90 average in high school. So all the students, if I took all the students with a 90% coming in from high school, what the average of them should be approximately 3.31. That's where the line. Some will do better than that. They'll have really high grade point averages, and some will do worse than that. They'll have a really bad fall term. I'm not talking about most students. I'm talking about the average of students. And it's never exact in terms of my prediction. And I have no reason to believe that they'll typically be above the line or below the line. About half of them will be above the line. About half of them will be below the line. Does that sort of help? What's the next one? So here's the same model. It had an intercept of minus 3.77. What does that mean? There's something wrong with the output. Students who only meet the minimum grade for admission will fail almost everything. The model explains only 3.77% of the grades, variation in high school grades, or none of the above. Intercept. So I've got a line, I've got an x-axis, a y-axis. The intercept is the value of y when x is 0. So if you have a high school average of 0, what will be your average, what's our prediction of your grades in the fall term at university? Minus 3.77? How can you have a negative GPA? You can't. But how would I have a student coming in whose average grade in high school was 0? That means every course they had 0 in. That doesn't make any sense. We don't have such students. Students need at least 70% to get in the door. You may make some exceptions, but you aren't going to go that far down to something close to 0. We've never seen a student down at that end. So it being negative, there's nothing wrong with it. Every straight line has an intercept somewhere. But we're never going to use this straight line down at high school averages of 0. So it's actually none of the above. So let's try one more. So the value of R square, that's my 0.29658 up. It means it indicates the model explains 29.7% of the variation in grade point averages. The model is weak and should not be used. The model will give accurate predictions 29.7% of the time, or the model gives predictions that are 29.7% too high on average. It is not a great number. If you're thinking of it as a grade, it's like a grade of 30% on an exam. It's not really good, but it's better than nothing. That it depends upon the context as to how low an R square is too low. Some people will use R squares that are down at 3% and quite happy with it. The model is supposed to represent the amount of variability, the noise that's present, that you've been able to eliminate or explain by putting a line through the scatter. So A is your right answer. So let's get on with trying to improve the model we had from last class. The easiest way to improve it is to include more information. We're only using the customer's credit rating. So we have other things we could use. We had seen that credit limit and income were also useful variables for predicting credit card balance. That we might, and credit limit seem to have a fairly high correlation. It seems that the more you allow people to borrow, the more they actually do borrow. Also, those with higher incomes have more money to spend, and they might choose to go ahead and spend it and use the convenience of a credit card to do so. They aren't worried about having too much debt because they have lots of money to go and pay it off. So let's try just adding one of those variables in. We'll pick limit because it had the highest correlation. So let's build a model that is, nope, I should have a last term in here in terms of noise that we've got. So the balance is an intercept. There's a slope term times the rating plus a slope term times the limit. And there'll still be some noise that we haven't been able to account for. Okay. So I'm going to do this in a minute. I'll show you how we do it in Excel. But Excel is going to ask, where is the Y variable, my target variable I'm going to try to predict. And I copied my variables into a new sheet. Limit, rating, balance, all into a new sheet, because these are the variables I want to work with. And so my balance was in my C column over here. And that's my Y range. The range is a column of numbers or group of numbers. And the X's are in two columns, in A and B. And it goes from A1, the top left corner, to B401 in the bottom right-hand corner. I'm including the labels, limit, rating, balance, in my formula. So I check off labels. And I can put this into a new sheet if I want. I'm going to go and put it on the same sheet, keep all that stuff together. Okay. That I've only got just this one model I'm looking at. So if I do that, the output I'm going to get, if you recall, I've got a couple of tables are going to come out. And the table I'm going to get is going to look like the one that I've got here. It has a summary of the model. This is the performance table up at the top. And at the bottom, it'll give me a table for the different coefficients in my model. And my model has got an intercept. It's got a limit as a variable and rating as a variable. Because I picked the labels on the columns, it's gone and put those in. So this is the coefficient for limit. This is the coefficient for rating. Okay. Now the model I had before was balance was minus 391 plus 2.57 times rating. This was from day 12's class. It had an R-square of 0.75 and a standard error of 232, rounding things up. So look at this new model. My performance measures, R-square, still 0.75, roughly rounded off. Standard error, still 232. It's not any better. It hasn't changed anything. My coefficients are a little bit different. It's minus 377 instead of minus 391. Ratings coefficient is now 2.2 instead of 2.57. But I got limited here. But this isn't any better than what I had before. Excuse me. So what's going on? Well, let's look at the limit, the coefficient for limit. It's 0.0245. Take a look over here. Here it is, 0.0245. And it has a standard error of 0.0638. It's important to look at those two. If standard error is a measure of how accurately I've measured that coefficient, and I'm saying, it's my best guess, but I could be off by 0.06. Worst case, I could be off by twice that, 0.12. Well, even if I was off by 0.06, either way, that would mean my coefficient could be as low as minus 0.04 or plus 0.09. Could be negative, it could be positive. Negative means that as with a higher credit limit will lead to a decrease in my credit card balance. Positive one says it could mean an increase in balance, or it could be something in between, like nothing, no change. There's no clear evidence that limit influences the credit card balance. I don't know if it's going up or down. I don't care about how fast it's going up or how fast it's going down. I don't even know what direction I'm traveling in. So it's not helping me. Why? Because it seemed before it had a very strong correlation. But if you did a scatter plot of credit limit versus credit rating, or credit rating versus credit limit, you're going to get almost a perfect straight line. If you knew the credit limit, you knew the credit rating. If I know the credit rating, I know the credit limit. If your credit rating is 600, then I think your limit is $8,000. That if you've got a perfect credit of 1,000, I'll let you borrow $14,000. But if your credit rating is down around 200, I'll only let you borrow $2,000. That if I know your rating, I know your limit. So it's not giving me any new information. So I said before, the way to improve a model is to bring forward new information into your model. And this isn't giving me new information. That what happens if I tried including income in my model? Okay, that what I would do is I'd copy rating and income and balance into a new sheet, and I'll go and build my model. I'll do that in a second. That what do I get here? Well, this was my old model, minus 391 plus 2.57 times rating, and had an R-square 0.75, standard error 232. Okay. Now remember, the highest R-squared you can get is 1. Perfect R-square. Okay. We're explaining 75% of the noise. Our goal is to get up close to 100%. Well, it says here my R-square is 0.875. So I've closed half the gap between where I was before and having a perfect model. Now, I didn't actually cut my error in half, though. It was 232 before. So is it going to drop down to 116? No. It drops down to 162, 163 or thereabouts. It's not perfect match up that way, but it's still a lot better. Okay. My R-square has gone up significantly and my standard error has gone down significantly. Maybe not enough, but it's a lot better than it was. If I look at my model, this is curious, that everything's changed. Intercept has changed, slope has changed. But look at the coefficient for income. It's negative. It says as income goes up, balance goes down. If you recall the scatter plot of income versus balance, people that had more money borrowed more. So it was a positive relationship. As income went up, balance went up. But now I've got a slope that's negative. It says if your income went up by $1,000, then your balance would drop by $7.67. What's going on? That, here was my scatter plot, income versus balance. That you have more money, you'll borrow more money. But now it's negative. Well, again, let's look at the variables in my model, income and rating. That if you've got a higher income, you get a higher credit rating. So I can't predict your credit rating perfectly, but I do know that you've got a higher rating. if you've got a higher income. Or if you've got a higher credit rating, you must have then probably a higher income. So if I know rating, I know something about your income. Not exactly. I don't know it as well as I know your credit limit. I have a good idea of what your income might look like. So rating is already capturing some of the information in income, but it's not capturing all of it. There's still some additional information in income that I am not capturing in the rating. But these two work together. So if I looked at two customers that if they're, one had a higher credit rating, or sorry, I had a higher income, that I might think they should have a higher balance, but at the same time, they would have a higher credit rating because of their higher income. I can't change one without changing the other. So I run into a problem here. If I go to change one variable, I'm going to change the other variable. And you may be used to looking at linear functions like a cost function that had to do with number of units of product A and number of units of product B. And your coefficients are the variable costs for product A and variable costs for product B. And you might think, well, if I make more of B, that has nothing to do with A. So I could look at its costs separately from A's. But now I can't. I can't look at changing one variable without changing the other because the two of them are linked together. They're very correlated with one another. This makes things really difficult. Or a problem of collinearity or sometimes multi-collinearity. It may not be just one variable affecting another, maybe a combination of them. But there's this correlation taking place so that I can't separate the impacts of them from one another. That I can't treat them separately. This, in value estimation, may not be an issue because we're just trying to make a prediction of credit card balance. But if you were trying to do a causal analysis, then it is a problem because I'd like to be able to talk about, well, what's the impact of changing customers' credit limit or changing their rating? Can I encourage them to borrow more? I'd like to be able to change variables separately from each other. So in causal analysis, if you've got correlated variables, it's going to make life more difficult for you. If you just want to make a prediction, it may not be a big deal. Now, the way we've been doing it is just by picking variables, finding the one with the highest correlation, throw it into the model. Okay, so I started out rating, I threw it first. Then I tried limit. Yeah, that didn't work. I threw it out, brought in income. Is that the way we should be going about this? Doesn't seem to be. We're getting surprises as we go, and that's not desirable. Think about the way you might go about problem solving or trying to make things better. You might look, say, I've built a model. My model's got mistakes in it, errors in it. Let me see if I can't find a way of reducing the errors. So I'm going to focus on the residuals. So in this case, here's one where my prediction was $500 too high. Okay, why? Is there a way I can reduce that error? So I'm not going to focus on the credit card balance. I'm going to focus on the mistakes I made with my model and try to predict the mistakes I'm going to make, anticipate them. And if I can anticipate them, then whatever process I use to anticipate them, I should use to build a better model. If I can explain my mistakes, then it means I shouldn't have made them. I should have been able to anticipate them. So one way of doing that is looking at what we call the residuals. Residuals are the errors. They're what's left over. You made your prediction and then what's left there that you couldn't explain. And so here was like my initial thing with credit rating and balance. And I put a line through a scatter. And I had points above and below and that sort of thing. And trying to look at this relationship may be difficult because you're looking at how things are moving. It's a moving target because the credit rating keeps changing, and that changes where the balances are. That if you look at the mistakes you've made versus rating, then you get a different type of chart. Call it a residual plot for rating. And you'll see it looks sort of different. Particularly, look at this funny line over here on the left. What's causing that? Well, if you look back over here, it's this line. It's the case when we've got a balance of 0. Now we get a balance of 0 at all kinds of different ratings. So that's why it's sort of a moving target here that didn't look quite the same back then. We can get these by asking for a residual plot when we build a model. Okay, that maybe I should go and do that. So let me get out of here. Hello. There we go. Let me hide you. So here was the stuff we had before. Let me just take our last model we had, okay, that we had income and rating. Copy these, give myself a new sheet, and I had balance. Okay. All right. So I've got my X variables together here on the left, and my Y variable on the right. If I want to do a plot, it makes it easier because I like the one I'm predicting to be on the right of everything else. Make this a little bit bigger. Okay. So if I went up to data, go to data analysis, computer's slow today, that I'm going to go down here to regression. Click OK. My Y variable, that's in column C, row 1 to C, row 401. And my X variables are from A1 over to B401. I've got labels, so I check that off. I'm going to put my output on the same sheet. Okay, so I'm going to click your output range. I'm going to put it in E1. So it's right beside me. And there's little boxes down here, residuals and residual plots. And I'm going to use these. So click OK. All right. This out of the way. Now, and the plots, they always stack them. So it's sort of hard to look at them easily. So here was the output that I had before, okay, I used to build my model with. And this was my performance stuff. The ANOVA table I don't pay attention to. And here's the one that had my coefficients that I used before. So here were the coefficients. This was my intercept value here. And then there was the coefficient for income and the coefficient for credit rating. I built that formula I had previously. And here are some residual plots. These are the errors in my predictions versus income and errors versus credit rating. It's different looking charts to what I had previously. We'll talk about them briefly in a minute. And if I scroll down, you'll see there's residual output. It has the observations. This is the predicted value. So this is the predicted balance. The first one, the prediction was 468.58. And what actually happened was 333. So 468 versus 333, I'm over by 130 some. So what does it say down here? There it is. That if I take the actual, subtract the prediction, that my prediction was too high by 135. So if I wanted to bring it back where it should be, if I take 135 from my prediction, I will get the 333 that I had before. And so minus 135, that would be some dot in here below the 0 line. On average, my prediction should be above and below the line in a balanced fashion. On average, the error in my prediction is going to be 0. Sometimes I'm high, sometimes I'm low. So these errors are what we call residuals. Go back to my slides here. Okay. So if I was to take those residuals that I just had a minute ago and copy them into a new sheet, okay, I took this one here as the residuals from the very first model, the one just using credit rating. So if I take my original model and I ask for its residuals, so this was the model with just credit rating as a variable, and I pasted it into a new sheet and then went back, took income, limit, cards, age, education, the other variables that I've got, and copied them into it, what would happen? So from the very first model I made, that was balance was equal to minus 300 and something plus 2.57 times rating. And I looked at the mistakes that model made. What's the correlation between the mistakes and the other variables? Well, here's residuals. Correlation with income is minus 4.35 or 0.435. That correlation with limit is next to 0. Limit's giving me no information. With cards, it's only 0.08. With age, it's minus 0.17. Education, it's 0.03. The strongest one is income. So income should be my next variable to add in because it's the best one at predicting my mistakes. And it's negative. That means that with high income people, I'm overestimating. My predictions are too high and I need to bring them down. That's why it's negative. But people with low incomes, my predictions are probably too low and I need to bring them up. So it's a matter of how your income is. As income goes up, I'm making more mistakes going down. That as I said, that limit gave me no new information. Correlation is very, very small, but income is valuable. So I'm looking at a correlation. I'm not concerned, is it positive or negative? I want the biggest number in absolute terms. Okay, and my biggest number is the minus 0.43559. Okay. My next choice would have been age. So I should add that into my model. Well, we added that into the model. And if I took the residuals that I just had a second ago in my new model with credit rating and income into it, and looked at the predictions, the errors in my predictions, and I looked at how do they correlate with the other variables, well, I get this sort of thing. The correlation between the errors and income, 4.75 E minus 16. What's E minus 16? That's scientific notation. It means move the decimal point 16 decimal places to the left, negative direction. That would be 0.000000000, a lot of zeros, 15 zeros, and then a 475. It's effectively equal to 0. So when you see E minus something really big, it means it's close to 0. Same thing happens with rating. There's, for all practical purposes, no correlation between the mistakes I'm making and what the income is and the rating. Why? Because we've taken all the information in income and rating to make our predictions. So there shouldn't be stuff left over there. But if I look at other variables, don't look at balance. I shouldn't have had that in the table. It's a nonsense number. If I look at the others, I'll find the, oops, there we are, with limit 0.007. No use to me. Correlation is very, very tiny. With credit cards, 0.014, almost 0, nothing much. Age, maybe if I put age in there, I'll make the model a little bit better, and it will. It'll make it a little tiny bit better. I'll go from an R square of around 88% to maybe 89 or 90%, a little bit more. Okay? Education, nothing there. That this is telling me that these other variables aren't going to add anything further to my model. I'm probably done as well as I'm going to be able to do with this basic model. Okay? So that looking at trying to improve a model, usually we can improve it by using more information, including more variables. But it has to be new information. So when I'm saying more information, it's tells me something I don't know already. And so if you've got a variable that you can already guess its value, like with limit, is not giving me new information, it's probably not going to help you. If you add a variable that's related to the one you've already got in there, or if you've got several to the several you've already got in there, you may find the coefficients end up being screwy. That this collinearity, multicollinearity problem becomes an issue. That generally when building, we like to start off simple and incrementally add variables. In your assignment, I got one that has a lot of different variables we could add, and each one adds maybe a little bit more information. That they, but the way you're doing it is generally you're going to look at the mistakes you're making, find of the variables I've got left to use, which ones are the best ones for explaining my mistakes. So I'll take the best one and add it into the model. And then I'm still going to make some mistakes, and I'm going to go back and look at, okay, what's the next one I should add in to explain the new mistakes I'm making? And I keep doing that until, sort of like this last case here, the correlations are really small. It doesn't look like anything is going to help improve my model. Okay? That these residual plots are really useful and informative in helping us see what's going on. Okay? Looking at these plots, this initial plot, there was that strange thing down in the bottom left that sort of curious, but the more interesting ones were after I had added in income into the model as well. Then when you start looking at it, look at this new scatter chart that we've got, scatter plot, that I've stretched it out a little bit compared to what I showed you in Excel a minute ago so that it's easier to look at. The ones in Excel are often too small for me. I like to expand them. And there are a few things happening here. This looks like a wave. This really dense scatter here. Something's happening here. And then above it seems to be floating a bunch of points. This is strange. That if I look at income, I've also got most of the points I should be centered around 0. Okay, that should be where my things are. And I should have an even band around 0. I should go up and down about the same amount. So like I went out about 250 above and below, and I drew 2 lines here. And it captures all of the negative ones, but it doesn't capture all the positive ones. The positive ones are really scattered over a big area. And if I go above 250, there's this bunch that's floating up there, sort of like I had with rating. That this scatter plot doesn't look right. It should be nice and symmetrical around 0, and it's not. Maybe there's a group of outliers that I've got. And maybe I've got 2 groups in my data set, and one is different from the other. And one accounts for the outliers. So we got a few things that we can do with this. That if I look at my scatter chart here, you might notice it does look like an S shape here for the rating, sort of like a stylized S. And so the after I looked at the scatter around the straight line, you'll see a bunch that are below the line, a bunch above the line, and then a bunch below the line. Well, it turns out when I look at those as residuals, I get these were the ones that were below, these are the ones that were above. Now I'm sort of below the line again. That I've got a wave here. I've got a curve. I don't have a straight line. So what do I do when I have a curve instead of a straight line? Well, that curves are not easy to work with because there's just so many different types of curves. You know, if you did trigonometry stuff in high school, sines and cosines and tangents and all that stuff, or polynomials, or you had ratio functions, there's a whole bunch of complicated curves out there, far more than you can imagine. And it's hard to tell, well, what sort of curve should you use? It's like finding a curved piece and trying to guess what did it come from. If you had a broken piece of pottery, what was it from? I don't know what the rest looks like because I've only got this little piece. That's what we have with playing with curves and data. Since our intent is to work with things that are simple, then the simplest type of curve is generally a polynomial. Polynomials are sort of nice. They're the things like quadratics with x and x squared in them. That with polynomials, they tend to be sort of like a sea serpent if it's a complicated polynomial. If it's just a quadratic, then it goes up, turns around, comes down again. Or it goes down, turns around, comes up again. It's got one bend to it. If you go to a cubic function with x cubed, it could have two twists to it. It's got a section that is concave up and another section that's concave down. And if you went to x to the power 4, you could have it twist one more time again. So I could use a cubic type polynomial because my curve that I had there a second ago, it's got a curve that goes this way and then it sort of twists the other way a little bit, not so strong. So a cubic might work for me here. One of the reasons I like them is when you look at it, it's a number times a variable plus a number times a variable plus a number times a variable plus a number. That's like a linear function. It's just that the variables all use the same x squared, x cubed. But in Excel, I could go and create new columns and do the same type of thing. Problem with this is that the credit ratings are big numbers. If I square them, if I take 500 and square it, I'll get 250,000, pretty big. And if I cube it, I'm going to get 125 million, I think, something like that. They get really, really, really big numbers. And you don't generally like to have numbers in your model that are very different sizes. Ideally, we'd like them to all be about the same size. So frequently we scale our variables. And this is not just when we have polynomials, it's generally when we've got variables of different sizes. So with this one, I'm going to do some scaling just to make it a little easier. And what do I mean by scaling? I don't mean just multiplying them by a number and making them all down. So, remove some digits. That the most common type of scaling is to convert things to z-scores. So I look at the mean score, and the mean rating is around 350. So I'll just look at, are you above or below average? Look at your rating and subtract 350. So if your rating is 500, then you're 150 above average. And then I'm even going to scale that, say, well, what's the variability, the spread of credit ratings? And the standard deviation is our measure of spread. It's about 150. So a z-score or a credit rating of 500, become a z-score of 1. And similarly, other ones will be scaled in this sort of fashion. And the nice thing is that generally the z-scores, most of them end up between -2 and +2. You'll get some that are further out, but most of them are going to be in that range. So when you square it or cube it, it's going to stay relatively small. And that's what we're going to do. We're going to find z-scores, and then we're going to square them and cube them. There are other ways you could scale, but this will make it a little simpler for me. And so that's what I did. I went and created a new column called z-scores for credit rating, ZRAT. And then I squared them and made that a new column, and I cubed them, made that a column. And so now I've got 4 variables. 2 of them are functions of credit rating, but I've got 4 variables in my model, and I'll just build it as a simple linear model. And that's what I did. And so what do we get? That we throw that in, my R-square goes up from 0.875 to 0.894. Little tiny increase. Not a lot, but a bit. My standard error is going to go from 162 down to 150. Down a little bit, 10% reduction in the error. And I get crazy coefficients. They've all changed. Okay, income is still negative, unfortunately. But it's a better model than what I had previously. That the error is smaller, so it should be giving me slightly better predictions. Okay. That I've still got the problem of collinearity between income and rating. Even though I've made it more complicated, it's still an issue, okay? This problem of not being able to explain different variables is still there. I can't fix that. That if I look at my residual plots, this is what I had before, this twist, and now it's still there. Maybe I have to go to rating to the power of 4, and that'll actually improve it slightly. Not much that you'd see, but it straightens it out a little bit more. I guess it's just more complicated than we thought. Okay, but it's not going to make a huge improvement. That we've still got other problems, and we're not going to deal with them all today. That this is already too long. But we still got this cloud up above, and it's even sharper to see it now than it was before. That this curve here is a little bit better defined than it was up in that one. So what's going on with this scatter? And that's what we're going to look at next class, is how we can get rid of these outlier points. Okay? And we're going to use some of the variables we haven't used. We've got nominal variables. Is it males versus females? Is it ethnicity? Is it being a student, being married? And then we'll try to run through one more time what's the process we've used. So that's it. I think we're all done. See if I can turn off the recording. I hope so. Anyway, bye now. Oh, I guess I didn't.